TechDaily.ai, your source for technical information. This deep dive is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup, disaster recovery, hyperconverged in VMware, Hyper-V, Proxmox cluster, AI servers, and public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com. Okay, let's unpack this. When we're building systems, things that need to talk to each other, like apps, websites, all that back-end stuff, there's this really fundamental choice you have to make.
Right. How do they actually communicate?
Exactly. Is it like immediate, a back-and-forth conversation? Or is it more like sending a message and just moving on, not waiting for that instant reply?
And this choice, synchronous versus asynchronous, it seems technical, but wow, it impacts everything.
It really does. How responsive things feel, how well they cope when things go wrong. It all stems from this.
Yeah, and it's not just implementation detail. It actually shapes the whole architecture, how resilient it is, how it can even grow over time.
Totally. And that's what we really want to dig into today. Our mission here is to get a clear handle on these two ways of doing things. Look at the trade-offs, because there are always trade-offs, right?
Always. No free lunch.
Exactly. And we'll look at some of the common protocols, the actual languages these systems use for these different styles. So whether you're deep in the tech weeds or just kind of curious how stuff works, this should be really helpful.
And you'll start seeing these patterns everywhere once you know what to look for, like paying for something online versus, say, uploading a huge video file.
Oh, yeah, good example. The expectation for speed is totally different.
Right. So this deep dive should give you that framework to understand why things work the way they do online.
Okay, so let's start with the first one. The immediate chat. Synchronous communication.
The ask, wait, then act model.
Yeah, pretty much. You ask a question, you stand there, you wait, you don't do anything else until you get the answer back. The classic analogy is a phone call, right? Both people have to be on the line at the same time.
That's a spot-on comparison. And in software, think about just browsing the web. Your browser asks a server for a page.
And it just waits. Spinning wheel sometimes.
Exactly. It waits for the response before it can show you anything. Or internally, between different parts of a big system, like microservices, service A calls service B and just stops, halts, until B replies.
Right. And, okay, there are good things about this. It feels, well, natural, like a normal conversation.
It's intuitive.
Yeah, and it seems easier to understand, maybe. Request goes out, response comes back. Simple cause and effect, which helps with testing, debugging.
Absolutely. If something breaks, the error, the stack trace, it usually points pretty directly back to the source of the call. That tight connection in time makes tracing what happened much easier.
You can follow the sequence.
Yeah. You know what happened right before, what should happen right after.
But, and there's always a but, this simplicity isn't free. What if the thing you're calling that service B, what if it's slow?
Yes. The dependency problem. If the service you're waiting on is slow, you're slow. You're stuck waiting.
You're blocked.
Totally blocked. And if that service is just down, unavailable, then your own operation might just fail completely. It's like gears meshing, one jams, the whole chain stops.
Right. And if lots of these calls are happening at once, the whole system can just grind to a halt or feel really sluggish anyway. Latency just builds up.
Exactly. So synchronous works best when things are predictable. Stable network, services you depend on are reliable, latency is generally low.
But it struggles with high traffic, or when response times are all over the place.
Precisely. That's the trade-off. You get that immediate clarity, that simple flow, but you pay for it with potential bottlenecks and fragility if things get busy or unreliable.
Okay, so that's the immediate back and forth. Now, the alternative, asynchronous.
Yeah.
How's that fundamentally different?
Asynchronous is more like sending a message and then just carrying on with your day. You don't wait for an immediate reply.
Send it and forget it. Well, not forget it, but...
Yeah, not quite forget it. But you don't wait. The classic analogy here is sending a letter through the post. You drop it in the mailbox, trust it'll get there eventually, but you don't stand by the box waiting for a response letter right then and there.
Gotcha. Okay, so tech examples. Where do we see this?
Oh, all over. Message queues are a big one, like RabbitMQ or Kafka. One system puts a message, like a task or some data, onto the queue.
And something else picks it up later.
Exactly, whenever it's ready or available. Also, think about event-driven systems. A service does something, maybe processes an order, and it just emits an event, order processed. It doesn't wait to see who heard it or what they did.
Like shouting into the void hoping someone's listening?
Kind of, but a more organized void, usually. Publish-subscribe systems work like this. You publish to a topic, and whoever is subscribed gets the message. The publisher doesn't need to know about the subscribers directly.
Okay, so what's the big win here? Why do this?
Decoupling, that's the magic word. Services can operate way more independently.
So Service A doesn't need Service B to be up and running right now.
Exactly. If Service B is slow or down for maintenance or just swamped with traffic, Service A can often just keep on working, putting messages onto that queue. The queue acts like a buffer.
Ah, absorbing the pressure.
Right. This gives you much better resilience. The system can handle bursts of traffic better. It can tolerate parts being temporarily offline. You generally get higher throughput for background tasks and better fault tolerance overall.
That sounds really good, like way more robust. So why isn't everything asynchronous? What's the catch?
The catch is usually complexity. It's not as straightforward.
How so?
Well, because things aren't happening in that direct line, monitoring gets harder. Tracking a single request across multiple asynchronous steps, that can be tricky.
Right, the cause and effect isn't as obvious.
Exactly. And errors might only show up much later, maybe in a completely different service, far removed from where the problem actually started. Debugging can be a pain. Plus, you introduce new infrastructure like those message queues. They need managing, monitoring, patching. It's more moving parts. And you often need specific patterns to handle things correctly, like using callbacks or event handlers to deal with the eventual outcome, or the outbox pattern to make sure database updates and message sending happen reliably together.
So you trade that upfront simplicity for more flexibility and robustness, but you take on more operational overhead and complexity.
That's a perfect summary. It's a fundamental trade-off.
Okay, let's nail down these core differences then. You mentioned time, space, and reliability before. Can we dig into those a bit more?
Sure. Time coupling first. Synchronous, as we said, needs the sender and receiver available at the same time. They're tightly coupled in time.
Like that phone call.
Exactly. Asynchronous breaks that. By using something like a queue, a buffer, the sender can send whenever and the receiver can process whenever. They're decoupled in time. The system tolerates delays much better.
Makes sense. The buffer smooths things out.
Mm-hmm.
What about space coupling?
Space coupling is about how much the sender needs to know about where the receiver is. In a synchronous call, the sender usually needs the exact address, the specific API endpoint of the receiver.
Like needing someone's direct phone number.
Precisely. With asynchronous systems, often using queues or topics, the sender just needs to know the name of the queue or the topic. It doesn't need to know who's listening, where they are, or even how many receivers there are.
Ah, so you can add more receivers, more workers processing those messages without the sender even knowing.
Exactly. That's huge for scalability. You can scale consumers up or down dynamically, much looser coupling in space.
Powerful. Okay, and the last one was reliability handling. How does that differ?
Right. In synchronous systems, if a call fails, maybe the network blips or the receiver throws an error, it's usually the client, the caller, who has to deal with it.
So the caller has to decide whether to retry or log the error or give up.
Yeah, the responsibility for handling that failure often lies with the client code. In asynchronous systems, especially those using a message broker, a lot of that reliability logic shifts to the broker itself.
How does that work?
The broker can be configured to automatically retry sending a message if the consumer fails to process it. It can ensure messages are kept safe, persisted, until they're successfully processed. It can handle putting failed messages onto a separate queue, a dead letter queue, for later inspection.
So the infrastructure takes on more of the burden.
It does, which is great, but again, it means that infrastructure, the broker, becomes a critical component that needs careful management and monitoring. It's not free magic.
Okay, summing that up. Sync is immediate, tightly coupled in time and space. Client handles retries. Async uses buffers, decouples in time and space, shifts reliability handling partly to the infrastructure. It's simplicity versus scale and resilience, basically.
That's the core tension.
Yeah.
And like we hinted, real systems often mix and match. You don't have to choose just one for everything.
Which is probably where the real skill comes in, knowing when to use which.
Absolutely. Designing those boundaries and interactions well is key.
All right, this is great. We've got the concepts down. Now let's get practical. How is this stuff actually done? Let's talk protocols, the nitty-gritty languages they use.
Yeah, this is where the rubber meets the road. Because the protocol you choose often pushes you strongly towards either asynchronous or asynchronous style, sometimes even a bit of a hybrid.
Okay, let's start with the big one, the foundation of the web, really. HTTP and REST, where do they fit?
HTTP is everywhere, right? And RESTful APIs built on it are, well, the default for so many things. Fundamentally, standard HTTP is synchronous.
Request response.
Exactly. You send a request to a specific URL, URI, and you wait. You block until you get a response back. And each request is typically stateless. The server doesn't remember you from one request to the next unless you use cookies or something.
So when my browser loads a page or my app fetches data, that's mostly HTTP doing its synchronous thing.
Yep. It's really common for basic data operations. Create, read, update, delete, CRUD.
CRD.
Yeah. And for that communication between the front end, your browser or app, and the backend server. Also very common for internal communication between microservices, especially when a little bit of waiting, a bit of latency is okay.
And the benefit is its simplicity.
Largely, yes. It's well understood, widely supported, relatively easy to debug. Tools are everywhere. Caching works well because it's often stateless.
But you mentioned limitations earlier, that blocking nature.
Right. While a service is just sitting there, waiting for that HTTP response, it's tying up resources, threads, memory, connections.
Doing nothing productive.
Pretty much. Under heavy load, that wasted waiting time can really add up and become a bottleneck. And retrying failed HTTP requests isn't always simple.
Why not?
Well, imagine you click place order. The request goes out, but you don't get a response quickly. Maybe it timed out. If you just blindly retry, did you place the order twice?
Ah, right. You don't want duplicate orders.
Exactly. So you need to think about idempotency, making sure that doing the same operation multiple times has the same effect as doing it once. It's achievable with HTTP, but you have to design for it carefully.
Okay, so HTTP REST. Great for immediate answers, low latency needs, simple interactions, but struggles with slow dependencies, high load, or complex background tasks where retries get tricky.
That's a good summary. Now, what about trying to get a more real-time feel? That leads us to something like WebSocket.
WebSocket, yeah, I hear that with chat apps, live updates. How's it different from just plain HTTP?
So WebSocket actually starts as a normal HTTP request, but then there's a special handshake, and it upgrades the connection to something different. A persistent, long-lived, two-way communication channel over TCP.
Two-way, so not just client asks, server answers.
Exactly. Once that WebSocket connection is open, both the client and the server can send messages to each other whenever they want, without the overhead of setting up a new HTTP request each time.
Ah, okay. So that's how you get live chat where messages just pop up or stock tickers that update instantly.
Precisely. It allows for that continuous bidirectional data flow, great for multiplayer games, collaborative document editing, dashboards with live data, anything where you need updates pushed from the server to the client without the client constantly asking, anything new yet? It feels synchronous to the user because the interaction is instant.
But it's asynchronous underneath, in a way, because either side can send anytime.
You could see it that way. The connection is persistent, but the message flow can be asynchronous. The main point is it's not the strict request-wait-response cycle of HTTP.
Got it. What are the downsides then? What are the trade-offs for keeping that connection open?
We have to manage the state of that connection. Is it open? Did it drop? Load balancers, the things that spread traffic across servers, need special configuration to handle these sticky, long-lived connections properly. They can't just treat them like short HTTP requests.
Okay, more infrastructure awareness needed.
Yeah. And importantly, WebSocket itself doesn't automatically guarantee that messages get delivered. If the connection drops while a message is in flight, it might be lost. You often need to build acknowledgement or retry logic into your application on top of WebSocket if you need guarantees.
So, ideal for that real-time interaction feel, low latency when endpoints are expected to be online, but maybe less suited for flaky mobile networks or when you absolutely cannot lose a message.
That's generally right. It puts more responsibility on the application layer for things like reliability.
Interesting. Okay, moving on. I keep hearing about gRPC. What's the story there?
gRPC. Yeah, it's definitely gained a lot of traction, especially for internal microservice communication. It's a modern framework from Google designed for high performance.
High performance how?
Several ways. First, it runs on HTTP 2, which is much more efficient than older HTTP versions. It allows things like multiplexing, sending multiple requests and responses over a single connection concurrently without blocking each other.
Unlike HTTP 1.1 where requests can block each other.
Exactly. Second, it doesn't typically use text-based formats like JSON. It uses protocol buffers or protobuf.
Protobuf?
Yeah, it's a way to serialize structured data into a compact binary format. It's much smaller and faster to parse than JSON, which saves bandwidth and CPU time.
Okay, so faster transport, smaller messages. What's the actual communication model? Is it still request response?
It's based on remote procedure calls RPC. The idea is that service A can call a function or method on service B almost as if it were a local function call in its own code. gRPC handles the serialization, network communication, and deserialization for you.
So it tries to make remote calls feel like local ones.
That's the goal. And it's strongly typed. You define your services and messages in a .proto file, like a contract. This generates code for both client and server, ensuring they agree on the data structures and available methods.
That sounds useful. Less chance of mismatches.
Definitely. Plus, gRPC has built-in support for different communication patterns beyond simple request response. It supports streaming. The client can stream data to the server can stream data to the client, or they can both stream bidirectionally over that single HTTP2 connection. It also has built-in concepts for things like deadlines, cancellation, and metadata.
So where does it really shine?
High-throughput microservice meshes. Internal APIs where performance and efficiency are paramount. Situations where you have services written in multiple languages. Protobuf has code generators for many languages. It gives you that performance edge over typical JSON REST, especially under load.
But is it still fundamentally synchronous in feel? Like you make a call, you generally wait for a result.
The basic RPC model is synchronous, yes. You make a call, you get a response or stream of responses. But because it's built on HTTP2 and has streaming, it's much more efficient than traditional blocking HTTP 1.1 calls. It sort of balances that familiar synchronous programming model with much better performance characteristics.
What's the catch? Is there a steeper learning curve?
There can be, yes. You need to learn protobuf, manage those .proto definition files, set up the code generation. It's maybe not as immediately simple to pick up as just firing off a REST request with curl.
Okay, so gRPC performance focus, contract first with protobuf, great for efficient internal comms, leverages HTTP2, but might take more initial setup and learning.
That's a good way to put it. Now, should we shift gears fully into protocols designed from the ground up for asynchronous messaging?
Yes, let's do that. Where do we start? AMQP.
AMQP is a great place to start. The Advanced Message Queuing Protocol. This one is really built around the concepts of reliable asynchronous messaging. Think message queues, guaranteed delivery, flexible routing.
And this is where tools like RabbitMQ come in, right?
Exactly. RabbitMQ is probably the most well-known message broker that implements the AMQP standard. AMQP defines concepts like exchanges, where messages are sent, queues, where messages are stored, and bindings, the rules that link exchanges to queues.
So it's more involved than just sending a message to an endpoint.
Definitely. It offers features specifically for reliable async communication. Things like persistent queues, meaning messages are saved to disk so they survive broker restarts. Publisher confirms, so the sender knows the broker received the message. Consumer acknowledgements, so the broker knows the receiver successfully processed the message before deleting it from the queue.
Okay, that sounds robust.
It is. And it offers really flexible routing. You can have messages sent directly to a specific queue or broadcast to multiple queues, fan out, or routed based on patterns in a routing key, topic routing. It also has mechanisms like dead letter queues.
The dead letter queues.
Yeah.
For messages that fail.
Precisely. If a message can't be processed successfully after maybe a few retries, instead of just being dropped, it can be moved to a special dead letter queue for later analysis or manual intervention.
So when would you absolutely reach for AMQP? What are the killer use cases?
Anytime you need strong guarantees about message delivery. Think background task processing, firing off jobs that must get done eventually. Inter-service communication, where you're triggering complex workflows that span multiple services and need to be reliable. Any system where losing messages due to temporary outages or failures just isn't acceptable.
So it's a heavy-duty option for guaranteed decoupled communication.
It often is, yes. Compared to HTTP's fire and hope, best effort delivery, AMQP provides mechanisms for eventual guaranteed delivery and durability. But that robustness comes with complexity.
Oh, the trade-off again.
Always. You need to manage the broker itself, which is a piece of stateful infrastructure.
Yeah.
You need to think carefully about retry logic, potential message ordering issues, how to handle duplicate messages if retries occur, idempotency again. It requires more operational maturity.
Makes sense. Robustness requires more careful handling.
Yep.
Okay, one more protocol that often comes up, especially with IoT, MQTT. How does that fit in?
Right, MQTT. Message Queuing Telemetry Transport. This one is designed specifically for situations where resources are tight and networks might be unreliable. Think small sensors, mobile devices. The Internet of Things is its sweet spot.
So lightweight is the key word.
Very much so. It's designed for minimal code footprint, low network bandwidth usage, and low power consumption. It uses a publish-subscribe model, similar in concept to some AMQP patterns or Kafka, but much simpler.
How does that work?
Devices, clients, connect to an MQTT broker. They can publish messages on specific topics, just strings like sensor one temperature, and shoot or subscribe to topics they're interested in. The broker handles routing the messages from publishers to the appropriate subscribers.
Simple pub sub. What are its key features?
Simplicity is key, but it also offers different quality of service levels, QoS.
QoS.
Yeah, letting you choose the delivery guarantee. QoS0 is at most once, fire and forget like UDP. QoS1 is at least once, guaranteed delivery but duplicates might occur. And QoS2 is exactly once, guaranteed delivery with no duplicates but more overhead.
So you can tune the reliability based on need.
Exactly. It also has features useful for unreliable networks, like persistent sessions, where the broker remembers a client's subscriptions even if it disconnects, and retained messages, where the broker keeps the last message published on a topic for new subscribers.
So ideal use cases are smart home devices, industrial monitoring, mobile apps on flaky connections.
Precisely. Anywhere battery life, bandwidth, and processing power are constrained, and you need simple messaging, often with unreliable connectivity. It prioritizes efficiency over the complex routing and stronger guarantees you might get with AMQP.
Got it. Lightweight, efficient pub sub for constrained environments. That covers a lot of ground on protocols. It's clear the choice really depends on what you're trying to achieve.
Absolutely. There's no single best protocol. It's all about matching the tool to the job.
Okay, so let's bring this all together. We've talked concepts, we've talked protocols. How does this play out in real-world system design? You said systems often mix these things up.
They definitely do. It's rare for a non-trivial system to be purely synchronous or purely asynchronous. You use the right pattern for the right interaction.
So when do you lean heavily synchronous? What kind of scenarios really demand that immediate feedback?
User authentication is a prime example. You enter your password, you need to know now if it worked. You can't wait for an email confirmation later.
Right, that would be terrible UX.
Totally. Many direct UI interactions, too. Clicking save on a form, maybe place order for the initial confirmation. You expect fairly immediate feedback that the action was received, or if there was an obvious error. Also, basic database reads or immediate writes where you need strong consistency right away.
So situations needing that strong consistency, predictable outcome, fast user feedback.
Exactly. Optimize for immediacy. But remember, that makes you vulnerable to those cascading delays if you chain too many synchronous calls together or if one service is flaky.
Okay, so when does async become the clear winner? Where do you absolutely want that decoupling?
Think about anything that doesn't need to block the user or the immediate flow. Order fulfillment after you get that initial order placed confirmation, which might be synchronous. The actual process of picking, packing, shipping, that can totally happen in the background asynchronously.
Yeah, I don't need to watch a progress bar for the warehouse picking my item.
Right. Sending emails or push notifications, generating reports, processing uploaded images or videos, resizing them, adding watermarks. Synchronizing inventory levels between your e-commerce site and your warehouse system. These are all perfect candidates for async.
Why? Because they might take a while, or they're resource intensive.
Both. They allow the main user-facing system to stay responsive. You offload the heavy lifting or the time-consuming tasks. Async optimizes for overall throughput, handling long-running jobs gracefully, and operating reliably, even if some parts are temporarily down, assuming you have retries and things set up right.
But the trade-off is, it's harder to see exactly what's happening moment to moment. Less immediate control.
Yes, visibility and immediate control are reduced, and you need that supporting infrastructure, the queues, the workers, and the monitoring to make sure it's all humming along.
Okay, what about hybrid examples? Where do you explicitly combine them?
Super common pattern. A web front-end makes a synchronous API call to place an order. The back-end API responds immediately with, "Okay, got your order, ID is 123.
So the user gets fast feedback.
Right. But then that back-end API immediately turns around and puts a message on a queue like process order 123. And separate worker services pick up that message asynchronously to handle payment processing, inventory updates, shipping notifications, etc.
The request acknowledge process flow.
Exactly. Or think about fanning out work. A single incoming request might trigger multiple different asynchronous tasks. You need discipline here, though.
Discipline out.
Clearly defining the boundary between the sync and async parts. Using correlation IDs, unique identifiers that follow the request through all its synchronous and asynchronous steps so you can trace the whole journey. And having really good monitoring and logging across the whole flow. The goal is always balancing that user-perceived responsiveness with back-end robustness and scalability.
It really sounds like a balancing act. Okay, let's step back even further. Beyond just performance and reliability, what other big picture trade-offs should people think about when choosing?
Well, we touched on performance and latency. Sync calls can block, cause queues, hurt throughput under load. Async can absorb spikes, improve throughput for background stuff. But async can introduce its own latency, the time spent sitting in a queue before processing. That might not be acceptable for everything. And there's overhead in just serializing messages, sending them, guaranteeing delivery.
Right. Nothing's free. What about reliability and fault tolerance, again, from that broader view?
Synchronous systems tend to fail fast. When a dependency breaks, you know immediately. Easier to detect initially, maybe, but as we said, higher risk of those cascading failures. One service outage takes down others.
Domino effect.
Exactly. Asynchronous communication provides insulation. Services can often keep working even if others are down, queuing up work. Better availability, usually. But you now have the responsibility of managing that queued work, handling dead letter queues, making sure retries happen correctly, ensuring idempotency so retries don't cause weird side effects.
Right.
Async is generally more resilient, but it needs more operational safety nets.
More robust, but needs more careful management. What about just understanding the system? Complexity and observability?
That's a huge one. Synchronous flows are often simpler to reason about. Request A calls B, B calls C. You can trace it fairly easily in logs. Debugging can be more straightforward.
Linear.
Yeah. Asynchronous systems, much more complex to observe. A message goes into a queue. When does it get picked up? By which worker? Did it succeed? If it failed, what did it go? Tracking one logical operation across multiple decoupled services and queues requires better tooling.
Like distributed tracing.
Exactly. Distributed tracing, good structured logging, metrics on queue depths, retry rates. You need more sophisticated observability to really understand what's going on end-to-end in a complex async system.
Okay, and what about the people actually building this, the developer experience?
Well, most developers learn synchronous programming first. REST and TTP is often the default. The tools are familiar, frameworks make it easy. It feels quite direct.
Lower barrier to entry, maybe?
Often, yes. Asynchronous messaging usually requires understanding more concepts, brokers, queues, exchanges, topics, maybe event sourcing patterns. You need to think differently, more about distributed state and eventual consistency. There are frameworks and platforms that help abstract some of this, but fundamentally it requires learning more about the infrastructure and patterns involved.
So sync is often more familiar. Key sync requires a bit more of a shift in thinking and tooling knowledge.
Generally speaking, yes.
Okay, so with all these trade-offs in mind, performance, reliability, complexity, developer experience, maybe we can quickly revisit those protocols, like quick heuristics.
Yeah, good idea. So based on all this, HTTPS. Choose it when you need clarity, simplicity, immediate request response. Great for standard APIs, front-end to back-end communication where some latency is okay. WebSocket. Go for this when you need that real-time two-way feel. Live updates, chat, dashboards. When low, consistent latency for interactive sessions is key. gRPC. Pick this for high performance, efficient communication, especially between internal microservices. When you want strong contracts, protobuf, and leverage HTTP2 benefits, AMQP. Use this when guaranteed message delivery and reliable decoupled background processing are critical. Task queues, complex workflows, enterprise messaging where you can't lose messages. MQTT. This is your choice for resource-constrained environments, IoT devices, mobile apps on flaky networks, when low power, low bandwidth, and simple pub/sub are the priorities.
And the key is choosing based on the use case constraints, not just what you used last time.
Absolutely. Don't use a hammer for every nail. Understand the requirements, understand the trade-offs of each approach and protocol, and then make an informed decision.
This has been incredibly clarifying. It really highlights how that fundamental sync versus async choice ripples through everything. So just to recap the big points, we've got the core difference, immediate wait versus send and continue. We've seen the strengths and weaknesses, simplicity versus resilience and scale. We've stressed understanding the trade-offs in performance, reliability, complexity, and we've toured the major protocols HTTP, WebSocket, gRPC, AMQP, MQTT, and where they fit best.
And the crucial takeaway is that often the best systems aren't purely one or the other, but intelligently mix both. using the right pattern for the right job.
Right. It's about that nuanced understanding and making deliberate choices. So here's something to think about as you go about your day. Using apps, browsing websites, try to notice the patterns. When do things feel instantaneous? When does something clearly happen in the background after you get an initial confirmation? Thinking about whether an interaction is synchronous or asynchronous, and why that choice might have been made, balancing that need for speed versus the need for robustness, it really gives you a different lens for understanding the digital world around us.
It really does. You start appreciating the hidden complexity and the design choices that make everything, hopefully, work smoothly.
TechDaily.ai, your source for technical information. This deep dive was sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup disaster recovery, hyperconverged in VMware, Hyper-V, Proxmox cluster AI servers, and public and private cloud. Check out stonefly.com or email your project requirements to sales@stonefly.com.